Okay, good morning, everyone. Thank you for joining. I'm going to talk on the BGW protocol, the protocol of Benor, Goldwasser, and Wittgenstein. So after the introduction of Yuval yesterday, we all know what secure computation is. Secure computation, we have several parties, A, B, C, and D. And essentially, whatever we want to, they all have some private inputs, and they want to compute some joint function of their inputs. And what secure computation gives us is that we can eliminate a trusted party. So whatever we can compute in a world where we have a trusted party, we can eliminate that trusted party and have a secure protocol, namely some specification of what's the next message is supposed to be, and we replace a world where just parties send their inputs to the trusted party, makes the computation for them, and gives them back the result with a secure protocol where we have some interaction that the parties do not learn anything, and they just learn the output itself. To put it in context, so we have set of parties, P1 to Pn. Each party has some private inputs, x1 to xn. Pi has input xi. And the parties wish to compute the joint function f on all inputs while keeping the inputs private from one another. The security properties that we want to have, so we have two types of adversaries in general. We have a semi-honest adversary. This is an adversary that corrupts some subset of parties. And these parties will follow the protocol execution, but they might look at whatever the messages they got and combine them and pull them all together, and they might try to gain some more information from the messages about the inputs of the honest parties. And malicious security, where we have an adversary that might act arbitrarily, it might lie, it might stop the execution in the middle, it might do whatever it wants. And our goals, our security goals, are as follows. So we want to have correctness, that the outputs of all of the parties are supposed to be according to the function. So even though we are not computing the function using a trusted party, we have a protocol, we have some communication. At the end, all parties are supposed to learn f of x1 to xn. We want to preserve the privacy of the inputs. The corrupted parties or the adversary should not learn anything about the honest parties' inputs. And we also want to guarantee, and this is only in the malicious case, it's actually an issue, we want to guarantee guaranteed output delivery. Namely, corrupted parties, even if they abort the protocol in the middle, they lie, they do stuff, they still cannot prevent the honest parties from learning and obtaining the output. So I'm going to talk on the BGW protocol, and the main result, the main theorem is as follows. So for any function, there exists a protocol that is perfectly secure, and for the semi-honest adversary, the adversary can control at most half of the parties, and for the malicious case, it can corrupt at most 1/3 of the parties. So for both of them, any function that you like to compute, these are the protocols. This is the threshold that we can afford to have. Just to put things in context, so yesterday Yuval showed this picture where what are the approaches to secure computation. We are going to talk on this linear secret protocols that are based on linear secret sharing, and specifically we are talking on the protocol of Benor, Goldwasser, and Wittgenstein. Okay, this is BGW. So I'm going to start to describe the protocol, talk a little bit about its security, and then I'm going to start with the semi-honest case. Okay, so as a warm-up, you saw this also yesterday in different slides. But let's say we have 4 parties, A, B, C, and D, and the parties wish to compute average of salaries or the sum of all inputs. Okay, these 2 functions are equivalent. So what was yesterday? What protocol did we see? So the first party can choose a big random number, R, and then it adds this to its input, this big random number. This is essentially essentially a one-time pad, right? Like I'm taking my input and I'm adding some random value to it. So what B sees is something that is completely random. Okay, B cannot understand what A's input is. We are working in a group where we have addition as an operation, so everything is think like modulus, some big number. Then B, where it receives X plus R, it just adds its own input, gives it to C, C adds its own input, gives it to D, and then D sends back its input to A. Now, the first party knows the random value, and it can subtract and obtain the sum. Okay? And then it can tell to everyone the sum of all inputs. What was bad with that protocol, what we didn't like? So this protocol is secure, but what we didn't like about it? Collisions, right? So if B and D are both collude, for instance, 2 parties that collude, so B knows what it sends to C, okay, we know exactly. It doesn't work. B knows what was sent, okay, what it sends to C. On the other end, D knows what it receives from C, so we can subtract its 2 values and completely obtain the input of C. We can obtain the actual value. So Yuval showed how to fix this protocol by having randomness between every pair of parties, and then one party adds some randomness, the other party some subtract, and all of them send this inbox and outbox together. I'm going to show a different way to do sum, and here what we are going to do, so each one of the parties first secret shares its input and gives 1 share to each one of the parties. So A takes its input, and it selects four shares, such that the sum of all of them is exactly X, and it sends to each one of the parties exactly 1 share. B does the same. It takes Y, it shares Y, and gives each one of the parties a share. C does the same, and D does the same. And what we have now is that each party holds exactly 1 share on the inputs of each other party. Each party now just sums all the shares that it has. So what I see is just completely garbage, but when I sum it together, it still looks garbage. Each party does it. And at this point, what we are doing, we are just going to send these shares to one another. And we are going to add all the values that I received from all other parties. Okay? Now, addition has this magic property that when you sum, when we sum elements, when we sum the rows, get a value, and then add whatever we have, or when we sum just the columns, and then after we sum the columns, we sum what we got, we're going to get the same value. Okay? This is magic property. And essentially, this is the protocol. And now this protocol is now we cannot, if two parties collude, they still cannot learn anything about the inputs of one other party. Okay? So I wanna say that what we have here is essentially the same template. It's going to be the BGW protocol. What we are doing here in the first round, we have an input sharing phase where each party takes its input and share it and give one share to each other party. Then we have the actual computation, where the actual computation just given all the shares, what is the function that I want to compute? It's sum, so I just sum all the shares that I got, okay? And then at the end, the last stage is output reconstruction. It's an output reconstruction phase. So given each party gets a share of the result, this is what we did in the actual computation, and then we just merge we reconstruct the output together. We send these shares to one another. Okay? So this is going to be, the same template is going to be in the BGW protocol. So overview of the BGW protocol. So first of all, we can look only on deterministic functions. Why we have this reduction over here. And our first step is to take the function f and represent it as an arithmetic circuit over some finite field f, okay, where the size of the field should be more than the number of parties. The circuit is going to have a lot of wires and some gates, and we are going to focus on, it's enough to assume that the gates are addition gates, namely if we have two wires A and B, A is some value in F, B is some value in F, and when we evaluate the gate, we're going to get the sum. Multiplication with a constant gate is you have some value, you can multiply it with any constants in the field, and this can be implemented using just addition gates, so I'm going to ignore multiplication with constant gates. And we also have multiplication gates where we have two values and we want to multiply them, okay? So this is how a circuit looks like. You have some input wires, okay? These are the input wires, these are the gates, and these are wires, and these are the output wires. And now evaluation, forget about secure computation. How do you evaluate a circuit? You first assign inputs on each one on the input wires. You want to evaluate f on x1 to xn. So I'm going to put x1 to xn in my input wires. Now the input wires assigned values. I'm going to go to the first layer, and when I see a gate, I know exactly what's the values on the input wires. I can compute the output on that output wire of the gate, and I can continue this computation gate by gate, layer by layer, until I get to the output wires, and I can actually learn the result. Okay, so this is forgetting about secure computation, how you evaluate a function. You can represent the function as a circuit, you can represent the function as a RAM program. In this BGW, we're going to represent the function as an arithmetic circuit. Yeah.
Why do you separate the and you don't do the same for addition? For the addition, previous time?
Yeah.
So you have this replace multiplication.
Yeah, so multiplication with a constant, we know exactly what the constant is, so you can implement it as having C additions, okay? So instead of looking at a circuit that has multiplication with a constant gate, I can look at the circuit where I don't have these gates at all, I just have much more additions, okay? With a constant, I mean, you know in the computation of F what the value of C is. Here, This one, it depends on the input.
Yeah, but you don't do the same. First of all, you don't do the same for addition.
What do you mean?
You don't separate your addition gates to addition with a constant and addition with an input.
Okay. It's just I want to say that you can multiply, you do linear operation. Like if you know C, you can.
C is the third x, or even larger.
It's what?
Does it not bother?
C is?
From addition or multiplication by a constant can take you a linear number of.
Yeah, this is a feasibility result. We want to show that every function you can compute. Okay? If you blow up a little bit the circuit, it's fine. But anyway, we can also support multiplication with a constant gate. You can do, okay. So we saw a circuit, how we evaluate, if we forget about secure computation, how we just evaluate the function. And now the goal of BGW is to do the same thing, but privately. So in secure protocol, each input wire is known, we can assume that it knows only to one party, okay? So P1 provides the input X1, P2 provides X2 to the computation, and so on. And each party also wants to keep its input private. However, when we compute the circuit, we don't want to reveal any intermediate value throughout the computation. So one might think that after you do you evaluate some gates, you can just continue with all the values publicly, but this is not okay. Every wire, every value on each one of the wire is supposed to be hidden. And at the end, only the output wires themselves, these are the only values that we are allowed to reconstruct and have them publicly. So the key idea of BGW is to emulate a computation on a circuit where all the inputs, with the inputs of the parties, and we are going to keep the following invariants. So the value of each wire during the computation is going to be hidden using some random polynomial of degree t. What does it mean? It means that the actual value on each wire is going to be secret-shared among the all parties. Okay? We saw that also in the toy example that we had in the sum. The function that we wanted, it has just sum of everything. And the wires are the input wires of the inputs of each party. And each party shares its input. That time it was not Shamir secret sharing. It was n out of n secret sharing. And then we did the sum and just reconstruct the output. So it's exactly the same template. Just a reminder, Shamir secret sharing. So we have Shamir secret sharing with threshold t. So we have a polynomial p where we put the secret at the constant term, and each party receives 1 point on that polynomial. And the properties is that every t plus 1 parties can recover the secret, and every set of t shares doesn't reveal any information about the secret S. So as I said, the overview of the protocol, we're going to have 3 phases. The first is input sharing phase, where each party shares its input to the other parties. Then we're going to emulate the circuit, emulate the computation gate by gate. Everything is hidden. No one knows anything because we're doing it on shares. And at the end, we're going to have the output reconstruction phase, where the parties reconstruct the values on the output wires and can actually obtain their output. So phase 1, stage 1, input sharing phase. Party PI has an input xi. So what it does, it just chooses a polynomial of degree t, that its constant term is its input, and is going to send to each one of the parties a share on that polynomial. Now it's important that party Pj, from all the polynomials of the other, it's going to always be evaluated on exactly the same point, exactly the same coordinate, alpha j. So each one of the parties, P1 to Pn, is going to be a value, alpha I, that's going to be assigned to it, and all parties are going to evaluate the polynomials exactly on the same point, coordinate. Next, the stage 2. Okay, so at the end of this stage, at the end of stage 1, each party is going to hold G1 on alpha I to Gn alpha I. I'm going to hold one share on each one, on a polynomial that hides each one of the inputs of all other parties. Then the second stage is the circuit emulation phase. We are going to show two protocols for two specific functions. One is how to compute an addition gate. So the inputs to that, now we are going to evaluate everything on secret sharing. So the input that the parties have, each party has one share of that wire and one share of this wire, and he wants to obtain a share on a polynomial of degree t that hides a and b, a plus b. Sorry. So this is essentially the function that we want to compute. Party P1 as the valuation of the polynomial on alpha 1, and the polynomial that hides b on alpha 1 also. And this is the input of P1. P2 has essentially the same thing on alpha 2. And then the last party as evaluation, it has a share on alpha n. And what we want to do is to evaluate the polynomial to have a sharing of a plus b. Okay? The same thing we want to do to multiplication gate, where the inputs are secret shared. So I have a share here and a share there, and we might have some interaction. And at the end, what we're going to have is a polynomial that hides a times b. We're going to have a share on a polynomial that is constant term now. It's a times b. Okay? In the circuit emulation phase, so we're going to use these two sub-protocols all the time. And we're going to emulate the computation of the circuit gate by gate. We're going to see, according to the circuit, where we compute shares of the output wire of each gate from the shares of the input wires, and using these two functions or two sub-protocols that we'll have to describe. At the end, stage 3, output reconstruction phase. So the parties hold shares of all output wires. What does it mean? That Pi, it holds a share on this wire, and share on that wire, and so on. Now we might have that all parties learn the same output, that the function has one output. We might have more general case where only P1 is supposed to learn Y1, only P2 is supposed to learn Y2, and so forth, so on. So what we are going to do is that all parties going to send their shares, so all parties know one share on each polynomial, and we are now going to give a party all the shares on that polynomial. So if P1 is supposed to learn Y1, each party has a share of Y1, so we're going to all send our shares to P1, and P1 can reconstruct Y1. Okay? And no one can share something else, can reconstruct something else. Okay. So all is left is to show these two, how to do this two computation, how to compute an addition gate and how to compute a multiplication gate. Once we have that, we finished. So let's take a look on an addition gate. So in an addition gate, I have a share of that wire, I have a share of this wire, and I want to obtain a share of some polynomial that hides A plus B. So what I can do is just add the two shares that I have. And now we claim that this is a good, this hides, this is a share on a polynomial of degree t that hides A plus B. So we have no interaction at all the parties do, they just take their two shares, add them together, and they claim that this is good. Why is that? So all the parties, what we actually compute here, we compute a share on this polynomial, okay? A polynomial that is defined as the sum of the two polynomials on the input wires. Because I have GA on alpha I, GB on alpha I, my sum is exactly a point on this polynomial. So this is a polynomial of degree t, and its constant term is exactly A plus B. Okay? So by just adding my two shares, we can evaluate an addition gate. How to evaluate a multiplication gate? So each party PI holds shares GA of alpha I, GB on alpha I. Okay, we are here. And we want to get a share on a polynomials that hides A times B. Can we just do what we did in the addition? Can we just take our two shares, multiply them together? Is that good enough or not? Okay, so what we will get? We'll get a share on the polynomial h of x, which is GA times GB, and its constant term is exactly A times B. So I'm asking if you just take your two shares for the multiplication gate and you multiply them together, is that good enough or not? Anyone? Right. So there are two problems with that actually. So one of them is the degree of h is now, it was supposed to be t and t. When we multiply two polynomials of degree t together, we get a polynomial of degree 2t. There's another problem that h is not, it's not really random. In particular, h is you can compose it, it's like composition of two polynomials, where a random polynomial of degree 2t is supposed to be, it has probability not to have anything like a prime, to have no divisor. Okay, so we have a problem. We don't know how to do multiplication so easy. So we're going to have some linear algebra to rescue us. So as a reminder from Monday, if you remember, we showed that there exists some linear combination where we take a point on a polynomial. There is a linear combination that gives us the constant term of that polynomial. Okay? Just to see why. So on Monday you had to use your imagination. Now it's on the board. If we take the van der Monde matrix and multiply by the coefficients of a polynomial, we're going to get all the valuations on all the points on the polynomial. Okay? We say that the van der Monde has an inverse if the alphas are distinct. And so we can multiply by the van der Monde, the inverse of the van der Monde from the left. And this is essentially what we get. So we can see that AB, there exists some linear combination that when you multiply, you do the inner product of this linear, of these lambdas, and the valuation of the polynomial on all points, you get exactly AB. This is what is written here. What is important that these lambdas depend only on the alphas. They are public, and alphas are public ahead of time. They are not secret. Everyone can know them. They can be part of the description of the protocol. So how we are going to compute fmult? So let's take again on this polynomial that we didn't like, that it was not so random, and its degree was 2t. And each party can compute a share on that polynomial. This is by just evaluating, taking my two inputs, taking my share on this wire, share on that wire, multiply them. I get a share on the polynomial h of x. A question, can we reveal h of alpha I to some other parties? Can we leak this value? The answer is no. It should be kept secret. Now we know what we had in the previous slide. That's AB. There is a linear combination of all the points on the polynomial that will give us AB. So the protocol would be to just, each party compute its two shares, multiplication of two shares. Then, given that multiplication, I'm going to share that value with each other party. So I'm going to hide h of alpha I using a degree t polynomial hix. Now each party has 1 point on each one of the polynomials of the others, and I'm going to output exactly the same linear combination that we did over here, now on the shares. Okay? And the question is why that protocols. So this is the old protocol for the multiplication. Very simple. I just multiply my two shares, share it with others. Given all the shares, we do some linear combination, and this is going to be the output. This is going to be my share on the output y. And why it works? So essentially what we are computing, remember that each one of these polynomials is supposed to be okay. Let's see. So what we are computing shares of this polynomial that's defined like that. Okay? Now each pi actually outputs, it evaluates that polynomial because pi gets h1 alpha I. This is the share that p1 gave me, and hn alpha I is the share that pn gave me. And when I'm doing this linear combination, I'm essentially getting a share on this polynomial. Now this is a polynomial of degree t. Why is that? Because each one of these polynomials, h1 to hn, is a polynomial of degree t. Okay? So linear combination of polynomials of degree t is a degree t polynomial. It is random because each one of them is random. And what's the magic is that its constant term is exactly AB. H on the constant term of H is exactly the linear combination of the constant term of each one of the polynomials, and each one of the parties was supposed to share exactly the polynomial of degree 2t, and this linear combination comes in and gives us exactly AB. So I just want to repeat again. The protocol for multiplication is very simple. I'm getting GA on alpha I, GB on alpha I. I just compute the multiplication of these two. Then I'm going to share that value with each other party. And each party, given all the shares, that just does these linear combinations on the shares, is going to obtain a polynomial of degree, a share on a polynomial of degree t that hides AB. Questions? Anyone? Because each one of the polynomials, I'm going to share this value with a degree t polynomial. Okay? And essentially what we are computing now is a share on this polynomial, and this polynomial is a linear combination of polynomials of degree t, so it is of degree t. Good? Anyone else? So it's not good, it's actually perfect. Okay, so for conclusion, what we get is it's a perfectly secure protocol for semi-honest, in which the number of corrupted parties is less than n/2. And I'm asking you, where did we actually use this honest majority? Just to see that. So where did we use it? Anyone? So in the multiplication, what we get is a degree 2t polynomial. So 2t, and the number of parties is just n, so we cannot afford 2t, that we still need it to be smaller than n, than the number of parties. Otherwise, we don't have enough information. Yeah? What? You can get a NOT gate from additions and multiplications. So it's out of the scope of this stuff. Okay. Security. So why is that secure, and where the security comes from? So essentially it's all secret sharing, and we love secret sharing, so the view of T parties doesn't give us any information on any intermediate wire. Let's take a look. So in an input sharing phase, I have my input, I share it with others. The adversary sees only T shares. As we, from the security of secret sharing, we know these T shares are going to look completely random. Then we have the circuit emulation phase. So addition is easy, we don't do anything. In multiplication, I'm going to again receive T shares. The adversary sees T shares on each one of those polynomials. Again, it's secret sharing, it's completely hiding the value, and these T shares look completely random. Only at the output, the corrupted parties receive some additional information. So given the T shares of the output wires of the corrupted parties, the simulator, it knows only the outputs of the computation, so it can fill the missing points on the polynomials for the reconstruction. So we can also simulate that last message of the output reconstruction phase. Okay? So this is security in one slide. I want to proceed to the malicious case. How much time? So this is the definition that we saw yesterday of the real ideal. I'm going to kind of write down what the properties that we need for malicious. So the parties are going to jointly compute f of x1 to xn, where honest party is going to provide their true inputs, but corrupted parties might provide any input that they like. And if they don't cooperate, the honest parties can just choose some default inputs for them. So we're going to have guaranteed output delivery. We are in a case where all parties receive the output. If corrupted party aborted, we're going to replace its input with something that all the honest parties are going to agree on. That's the only requirement. The privacy is the adversary doesn't learn any information on the honest party's inputs, as always, and guaranteed output delivery, as I mentioned. So if we take a look at the semi-honest protocol, what might go wrong? Where the adversary can do something. So what might go wrong in the input sharing phase? In the input sharing phase. What might the adversary do? Send garbage. That's it. I'm supposed to send a degree t polynomial, points on a degree t polynomial. Instead of that, I'm going to send something that is not, do not lie. The shares do not lie on degree t polynomial. Okay? Then, during the surrogate emulation phase, what might go wrong? So during the addition gates, nothing can go wrong because there is no interaction. Multiplication, we'll see, we'll elaborate on that in a second. What might go wrong in the output reconstruction phase? Again, we are considering the semi-honest protocol and trying to understand what might go wrong. So what might go wrong in the output reconstruction is just that parties might send wrong shares to one another. Instead of sharing the actual value that they have, I'm sending something else. Okay? How to fix these two, input sharing phase and output reconstruction phase, we saw that on Monday. We talked about the VSS, the verifiable secret sharing protocol. So we showed that if t is less than n over 3, we showed that there exists a verifiable secret sharing protocol in which if the honest dealer is honest, if the dealer is honest, then the adversary learns nothing about the secret. And if the dealer is corrupted, the honest parties receive shares that are consistent with something. It's not necessarily the input that the dealer wanted to put in. If it doesn't behave according to the protocol, we might end up with different secret, but we must have a degree t polynomial. Must have shares on a degree t polynomial. And correctness requires that if the dealer is honest, what I wanted to input to the protocol, this is what we are going to end up with. What about the reconstruction? So we say that all the points on the polynomial are just a Reed-Solomon. It's like an evaluation of a Reed-Solomon code. So if corrupted parties send some wrong shares, honest parties can still recover the secret. Okay? Even if I get a corrupted code word, I can still correct and get the output. What it means that if parties here send something garbage, there are only t mistakes that we are going to have, and so we can error correct and get the true value. Okay, so before we proceed, forget about the multiplication. Multiplication will have to work hard. Note that already we have a lot of functions that we can compute. Note that if the function f doesn't have any multiplication gate, we essentially have already a malicious protocol. We just have to plug in VSS instead of secret sharing, of Shamir secret sharing in the semi-honest. And essentially what we can compute is all linear functions. So we can take x1 to xn and get a linear combination, or multiplication with a matrix where we have some input, we multiply the matrix with the input, and each party receives an output. So these are functions that we already know how to compute in a malicious case. So again, what I'm going to focus on now is how to do with multiplication. So let's take a look again on the multiplication gate of semi-honest and tell me what might go wrong here, where we might have some, where the adversary can cheat. Okay, so remember, each party has a share on the input wires. I first multiply my two shares, and then I'm taking this share of polynomial of degree 2t, and I sub-share it to the other parties. Each party gets a sub-share on that polynomial. And given all the shares that each party receives, we just do some linear combination and get a share on the output wire. Okay? What might go wrong here? What is the communication? So the only communication that it's not the only interaction that we have is in this step. So this step has two different things. First, it might send a polynomial that is not of degree t, but we know how to deal with that. How we deal with that? VSS. The second thing that we might have is that the secret that we input into the VSS is wrong, and this is the actual problem of the multiplication protocol. The corrupted party, it was supposed to subshare the multiplication of its two shares. Instead, it's going to put something else. Okay? So what we'll want to have, or how the malicious protocol will look like, is between these two instructions, we're going to have, after each party subshare it's the multiplication of its two shares, we're going to have some verification in which we're going to verify this, that what was input, what the input was correct. I'm going to look on a simplified case where t is less than n over 4. I'm going to describe also why it's going to simplify our life. But I want to mention that there is a different protocol, a little bit more sophisticated, that it's for t less than n over 3. So let's take a look at this polynomial h of x, which is the multiplication of the two polynomials. And now each party subshare its share on that polynomial, where one party or some parties, t parties, might subshare values that are not on that polynomial, that might put something else. When t is less than n over 4, let's take a look at the case where n is actually 4t plus 1. So we want to somehow verify that all the points that were subshared actually lie on the same degree 2t polynomial. If we have that, then the linear combination of everything is going to be correct. So recall that points on a polynomial is just a word, a code word in a Reed-Solomon code. And Reed-Solomon code is n, k plus 1, n minus k code, which means that you take a word, you take a message of size k plus 1, you increase it to size n, you get some redundancy, and the distance between two code words is n minus k, which means that we can correct essentially half the distance. When we put n equals 3t plus 1, the case of t less than n over 3, what we get is a code word where the distance is t plus 1, which means that we can correct t over 2 errors. Again, I'm looking now on a polynomial of degree 2t, not on a polynomial of degree t. Okay? So when we look at a message which was 2t and was enlarged to 3t, the distance is t plus 1, and so we can correct t over 2 errors. But when we have only a quarter of the parties are corrupted, and we are taking a polynomial of degree 2t and going to take that as the code word, we can correct now t errors. And this is why the case of t less than n over 4, much easier. We can correct more errors already here. So essentially, what we would like to do is that after each party subshare its share over here, we want to somehow correct this degree 2t polynomial to recognize where the errors are and eliminate those errors. Okay? So I'm going to use some facts from error correcting code. If we have C as an NKD linear code, in order to generate, we take a message, we want to encode it. The encoding algorithm can be described as just multiplication with some generator matrix G. Okay? In Reed-Solomon, this generator matrix is van der Monde. Moreover, there is a parity check matrix that when we get elements in the code word, we can identify if a message of size n is on the code or not. A parity check matrix is a metric that satisfies this equation, g times h is all zeros, which means that when we take a code word, something that actually has a pre-image, then C, we can describe C as some message times G. So some message times G, and G times H is 0, so we're going to get 0. And if we got a noisy code word, some code word that some error was introduced, when we multiply a noisy code word with H, this is what we are going to have. So C times H is going to be 0. Okay? So we are left only with E times H. And what is nice, another fact from error correcting code, that we can extract E from E times H times T. And the important thing is that E times H doesn't contain any information about the message M. We essentially, by multiplying with H, we are losing all information about the message itself. So in our simplified case, each part is going to multiply its two shares. It's going to sub-share it, and then, yeah. So you have the actual value here, the actual polynomial. When I multiply now with H, you're going to get all zeros on all the correct elements, and only those are going to show up and see what error was introduced. If you will also receive, like, what are the actual values there, this is bad. Okay? This is what you want to hide. So, so we had a noisy code word over here. We are going to multiply with H, and then we are going to run a check, and if someone introduced something that is wrong, we want to identify it and remove that error and eliminate the error. Let me just describe this check. So we saw that the check is just a multiplication with a matrix, right? Multiplication with a matrix is a linear function. And we know how to compute linear functions. Linear functions, we said, you do VSS, you evaluate your points. It has no multiplications. Okay? So I want to describe the protocol. So each party takes two shares, multiply them, and now I need to sub-share those values. So P1 is going to sub-share H of alpha 1 using polynomial capital H. Okay? So each P1 sees, the columns are going to be the shares that each party receives. So P1 receives this share, P2 receives that share, and so on. The second party also sub-share its share. At the end, here, someone is going to introduce a bad share, bad value. So it's going to do VSS on a value that is incorrect. So what each party is going to receive, they're going to receive shares on a polynomial that instead of hiding H alpha I, it's H alpha I plus some EI. And we're continuing, and each party has all the shares. Okay, this is the shares that P1 receives, and so on. Now we want to identify that the sub-shares that we have over here are incorrect. And as we saw, the first thing that you do in BGW is sub-share your inputs. You do some evaluation and reconstruction. So if you wanted to compute the evaluation of this code word with the parity check matrix and learn the errors, the first stage would be sub-share each one of the inputs. Now do evaluation, which multiply our subshares with the matrix H, the parity check matrix of the code, then we can get the errors and see that all those values are correct, but this one has an incorrect value. So the parties can reconstruct this error vector, and now when I see the error vector, I can just reconstruct this matrix, this polynomial, and learn H alpha I plus EI. I also know alpha I, and each party can just get shares on those on a constant polynomial that equals H alpha I everywhere. So for conclusion, multiplication with n equals 4t plus 1. So each party holds GA alpha I, GB alpha I. Each party multiplies the two things. Then we have to subshare H alpha I. And we are going to multiply with this, everything on shared values. We're going to multiply with the parity check matrix, reconstruct the output, and realize which inputs were correct and which were wrong. And then what we're going to have is going to have subshares on the right values that adds the right values, which are the multiplication of GA alpha I, GB alpha I, and we can run this lambda, this linear combination to get a share on a correct output. Okay? So the question was if it was identifiable abort. So if party aborts, I can identify. If it's cheated, I can identify. This specific thing, yes, but there are other places where party can cheat, but it doesn't really influence the protocol. So I'm not sure about the definition. Like in the VSS, I can give you a wrong complaint that doesn't do anything later. Okay, what happens when n equals 3t plus 1 and not 4t plus 1? What happens there is that this thing we cannot do anymore, this correction of the wrong inputs. Okay? So we cannot just multiply our two shares and then correct the inputs, because as we saw, we don't have enough. We cannot correct a polynomial of degree 2t when all the points that we have are 3t plus 1. Okay? So when we have only 3t plus 1, we can correct only 2 over t errors in a polynomial of degree 2t, and we might have t errors on that polynomial. So instead, we're going to add 2 more sub-protocols. So first of all, instead of sharing H alpha I, which is the multiplication, we'll have to first subshare GA alpha I and the share GB alpha I. And here we can do the same correction that we did before. Here we can do this verification that all those shares are on a degree t polynomial. And then here, between these two stages, each party is going to prove that what is going to share over here is a multiplication of 2 values. And this is another sub-protocol. So we're going to use the sub-protocol that we saw for the error correction over here on the degree t polynomial. And there's another sub-protocol that I didn't show how to do this verification over here. So the main theorems are, we saw perfectly secure protocol in a semi-honest model for t less than n over 2. We saw a malicious protocol for t where n less than, when t is less than n over 4. It holds that the BGW also holds when we push the threshold to n over 3. And I just want to mention there is also statistically secure if you assume broadcast when you go to n over 2. And with that, I'll conclude. Thank you.